This is physics 1102. Exam spring 2023. Exam 5 review on chapters 27, 28, 30, and 31. I'll go through what each one is briefly. Models of the atom. All right. Chapter 28. And the Bohr model, including the Bohr model. Quantum mechanics of atom. All right. Including the periodic table, exclusion principle, and such. We're skipping chapter 29. Then we have chapter 30 is nuclear physics. And radioactivity. And then finally, chapter 31, which is the last chapter for the year. Nuclear energy. And radiation. So this includes dangers of radiation, health effects, what kind of radiation we get from that. As far as labs are concerned, lab 11 is covered. Gas spectrum. Which is sort of covered from the last exam. Lab 12. And that is on a black body. Radiation. And also deal with the Bohr atom. Okay, and Bohr atom. Simulations, and then lab 13 is on radioactive decay lab. All right, so that's what the chapter exam is on. Again, it'll be about 15, 16 problems, and then problems about 5 to 6. All right. So this will be the final exam for the year. Again, we're dropping the lowest exam score out of the 5, and then the final will be comprehensive. I'm not going to do a review for the final. The final is approximately 100 questions, all multiple choice, covering all the topics from the year. So, check the date for this exam, and let me know if you have any questions. Okay, so, moving on here. So let's look at chapter 27. All right, we've been through all this, so we'll just go through electron. All right. Discovery of it was in 1897. By J.J. Thomson. And what he was able to observe, with the electron charge measurement, is electron has a charge, Q, we call E, is minus 1.6 times 10 to the minus 19th coulombs, and has a mass of 9.1 times 10 to the minus 31st kilograms. We'll get into the proton later, but the proton has an exact opposite charge, 1.6 times 10 to the minus 19th coulombs, and a mass of 1.67 times 10 to the minus 27th kilograms. So that's later on there, as far as that is concerned. All right? So, next part is on black body radiation. Meaning radiation that a hot object puts out, as we see here. So the amount of radiation goes as the fourth power of the temperature. So the power radiated is proportional to the fourth power in degrees Kelvin. Meaning, if you, as you've seen, if you double the temperature, so then the power is going to be 2 to the fourth as much, or 16 times. So 2 times 2t goes to 2 to the fourth on the original, or 16 times. All right. So you'll see that from the handout. We also have on black body radiation the peak wavelength. Lambda p is such that lambda p times the temperature is 2.9 times 10 to the minus third. So if the temperature increases, the peak wavelength is going to get less and less. Okay? So a hot object radiates more energy in the higher energy, shorter wavelengths. All right. We talked also earlier about photoelectric effect. Right, and that's in the lab. All right, so photoelectric, which was discovered by well, not discovered, but it was understood by Einstein. Again, E equals H times F, where H is Planck's constant, 6.6 times 10 to the minus 34 joule seconds. So we talked about that already. And light is in photons, so we've been through all that. We also have light momentum. Which is P is H over lambda. So any particle has a wavelength associated with it, but we only see this effect on really can measure it for very small particles such as proton, or electron. Every day, large objects, there's still, as we've seen from the lecture for this chapter, a wavelength, but it's so incredibly small that it's immeasurable. Let's see here. That's about, yes, we have the wavelength nature of light. So momentum, h times h over lambda. And it's because of this that we have, for a light microscope, traditional microscope we've seen, all right, minimum, you can get down to about, let's see, 1 micron, 10 to the minus 6 meters. But electron microscope, you can get down to about 1 nanometer, or 10 to the minus 9th meters. Far more accuracy using electrons as the light source for electron microscopes. Okay. We also talk about atomic spectra. All right, so we talked about atomic spectra like we've done before. All right, and the question is, how does this come about? That's where we went into the Bohr atom, the Bohr model. Okay. And given by, let's see, we're going to have a formula. Right, where each orbit corresponds to different energy levels, so that's that. And we get the quantized energy levels as we saw, and we can calculate them. So again, the visible is the Balmer series, ultraviolet is Lyman series, and the infrared is Paschen series. So that's pretty much chapter 27 is concerned. All right, we have the lab that goes with this as far as the Bohr model. All right, moving on to chapter 28. All right, we have uncertainty principle. We talked about, and this is where you can't, because you have to use light to interact with measuring where an object is. If you know precisely it is, you can't know its momentum. Again, this is delta x times change of momentum is greater than or equal to h. Okay, approximately. Again, h is very small number. So this is called the Heisenberg uncertainty principle. As we've done, then we had, all right, 28.6, our quantum numbers. All right, exclusion principle. And periodic table. which explains why the periodic table is where it is. All right. Get different numbers, N, L, M sub L, and M sub S, which are the 4 quantum numbers to account for electrons. And from there, we end up with the periodic table and electron configuration. So like for hydrogen, it's just 1p. For a 1s, I should say, because the states are S, P, D, F, and so on. So 1s. For helium, 1s2. For lithium, 1s2, 2p1, meaning it's the next level up, and so on. So questions will be writing down what the electron configuration is for a particular element, the entire configuration. And that's pretty much it for chapter 28, all right? So the main thing is quantum number, the periodic table, what quantum numbers are, and how this leads to the periodic table, and electron configuration. Okay. So now know what those mean. All right, so that's in chapter 28. All right, again, we're skipping chapter 29. So next one will be chapter 30. We're moving into radioactive decay. So, and again, this is based on the so-called binding energy. So as we mentioned earlier, so elements greater than iron 26 will benefit by radioactive decay, meaning they'll break down the smaller ones less than, like hydrogen, helium, and so on, fuse together to produce energy as far as that's concerned. Okay, so we talked about radioactivity. All right. Alpha decay, again, alpha. So, such as radium 226, 88, breaks down to radon 222, 86, plus a helium nucleus. All right? Beta decay is example of carbon-14, breaks down to nitrogen-14, and releases an electron. All right? So carbon, this is radioactive, so I use carbon dating, goes back to nitrogen, which then also releases electron, which we call beta charge. And then the last one, a gamma decay, gamma radiation. Which is a gamma. I'm not going to get into it because this is kind of complicated, but that's at a very high energy photon. So it's a photon instead of a particle per se. All right, this is what's emitted, emitted, emitted. And in terms of danger, what you'll see is alpha radiation. Because it's so large, it's only dangerous if it's absorbed into the body. Beta can be a little bit. Gamma rays can be very dangerous as far as penetrating into the body. We'll get into that. We have half-life. And half-life is N0, N. So we in half-life. So we have an N is N0, e to the minus lambda, which lambda is a decay constant. But if we do it in terms of half-life, then it's going to be, let me get to that. Time, so this is a decay constant. And T half-life is 0.693 over lambda. And we talked about radioactive decay, which is every half-life, half of it's left. So one half-life, you get half. 2 half-lives, you get a quarter left. 3 half-lives, you have an eighth left, and so on. And that's what leads to radioactive dating using carbon-14 for organic substances. Things are alive at one point, or we use longer like uranium and such that have a higher half-life, longer half-life for dating rocks and such. But the main thing is like carbon-14 is interesting because it says a half-life of 5,730 years. So that's why that was able to be used. So you look at the problems related to that. The problems would be primarily dealing with like half, quarter, and eighth, and so on. So if you start with 100 atoms of carbon-14, how many do you have after 1 half-life, 2 half-lives, and so on? And that is chapter 30. So basically it's on radioactive decay, alpha, beta, and gamma, radiation, and half-lives, as we talked about already in chapter 30. All right. In the final chapter of the year, this is on nuclear energy. And the lab on nuclear energy. So we have fission, right, which is the basis for the atomic bomb. And then fission, a fission reaction, you have, I'll just show you, there's so many numbers, it's kind of detailed, but again, for a fission reaction, neutron strikes a uranium-235, which produces barium and krypton, and 3 neutrons. So as we talked about already, 1 neutron hits uranium, which splits into particles, but more importantly, produces 1, 2, 3 neutrons, which can hit other uranium. And again, this is on the order of about a billionth of a second, so rapidly. So these can each lead to 3, and it rapidly explodes literally very quickly. So that's nuclear decay, nuclear reactions. A little bit on a bomb. As we said, need about 80% U-235 because 238 doesn't work. Remember, 230 uranium itself is approximately 1% uranium-235. So part of the big problem of developed bomb is try to separate this from uranium-238. All right, so 99% is this approximately. So that was the whole basis of the Manhattan Project. For a reactor, it's much, much less, maybe on the order of 4%. Yeah. So for the reactor, about 4% U-235. So a bomb, you have to have that. If you looked at the lab, you had to get the amount of uranium-235 very high to be able to have that occur. So that's nuclear fission in reactors. All right, so that's fission as opposed to fusion, which is part of what we see in the future. So fusion, and in fusion, basically you have a hydrogen plus hydrogen combined to make helium, and the helium weighs less than the original hydrogen, so plus energy. And actually a lot of energy based on Einstein's E equals mc squared. So that's one process of fusion. Right, there are other ones. I'm not going to get into those right now. All right. And so fusion, fusion is far more efficient than fission, but the problem is this is what occurs in the sun. As we've said, not going to get into the process of that. And all right. Then we had health effects. Of radiation, all right? Background, radiation. Different types of radiation. So again, from alpha radiation, which one example is radon, decays to radium and produces an alpha particle. And because radon is a gas, it's rather, you get these, it's rather dangerous. So the radon decays and produce, so this is radioactive. Gas, as we said, so this is one product, another one is plutonium. Very dangerous as alpha radiation. So as far as, but this is only dangerous if it's ingested. The next one is beta radiation, which electron, and then finally the most dangerous ones, which can penetrate the skin, is gamma radiation. And so part of it is as you talked about, as far as that's concerned. So, okay, so that's all for chapter 31. All right, so again, the exam is on chapters 27, 28, 30, and 31.